Hello everyone, I am Shirish Pathak and in this lecture we will discuss about projectile motion using vectors. So this is not a very common topic you will find everywhere in your normal classrooms and general coaching materials. These are like some special parts of the chapter which are normally not discussed in everywhere. So we'll see the expressions we encounter in projectile motions. So those are time of flight, range, maximum range analysis, and all three kind of we'll repeat in the fourth part, which is projectile on inclined plane. Theoretically, things remain the same, but we have an inclination, so I'll discuss it, or maybe I'll leave some of them for your own understanding. Okay, so we'll begin with general theory of vector. How do we represent vector equations? How do we represent equation of motions using vectors? Okay, so we have three. Broadly, we have three equation of motion. V equal to u plus at, s equal to ut plus half at square, and the third one is v equal to u dot u plus 2 a dot s. But we won't need this third equation in our today's analysis. So these are the two we'll see today. And since we are discussing about projectile and gravity, only gravity, so we can replace A with G. So one by one we'll start with each of them. We are discussing only about the first two, and another one we will derive from these two only. Okay, so for representing different vectors we are using different color coding. Like I can represent final velocity vector with yellow color, initial velocity vector with red color, operators with white color, and scalars with white color. Okay, now how do we read this? We read this in this way so that we can interpret it geometrically also. We'll read it like v vector is u vector plus g vector scaled by tau. This is nothing but v equal to u plus at only. But since we want to interpret this geometrically, we are writing in this way. Okay, so now we'll draw the vector diagram for this. First of all, we'll draw u vector. We assume this much is the magnitude of u and this is the direction of u, because we don't know it right now, so we can draw it anything random. Now, but for gravity part, we know the magnitude of gravity should be 9.8 meter per second square. But since we are scaling it with tau, so the length is not fixed now. It may vary with time, linearly, of course. Since we want to add these two, I'll start the tail of gravity scaled by tau. By gravity, I mean to say acceleration due to gravity. I'll mark this vector. Now we know by triangle of addition that sum of these two vectors should be this one. And according to the equation, the sum of these two vectors was v vector. So this is obviously the v vector. This is g vector scaled by tau, and this is u vector, which is initial velocity vector. I'll write it now. This was u vector, this was g vector scaled by tau, and this was final velocity vector. Okay, so now we have a vector triangle. So we can use properties of triangles and solution of triangles to find out various things, like angle between some of the angles are given in the question and some we want to find, or we may find the length, which indirectly gives us the vector part only, length of the vector. Okay, now when we do geometric analysis, like we use SOT, POT, and those things, then we consider these vectors as normal. These vectors had something with their magnitude itself, not the direction property. Now this is a triangle. We want to find sides or angles. We'll directly use the side thing, not the direction thing, only the magnitude part. Okay. So now we'll see the other equation. How do we plot? How do we draw it? The other equation was, just a second. The other equation was S equal to so the other expression was S vector equals to U vector, initial velocity vector, scaled by tau, plus G vector scaled by half of tau squared. This is the thing we are talking about. Now we will draw this thing also. See, this time when we were discussing about this part, we had this u vector with constant magnitude. Why? Because magnitude of u vector is already fixed. But when we see in this part, it's not fixed anymore because it is scaled by tau. So again, it varies linearly with time. So again, we won't have the fixed magnitude until and unless tau is fixed. So we'll draw it again. Maybe this one is the u vector. Similarly, we'll draw the g vector also, g vector part. See, the length can be anything, this much, or this much, anything. Like, let's consider only this much. So now the displacement will be the sum of these two, and by triangle law of addition, the sum should be along this vector. We'll draw it using blue vector. This is u vector times tau. This one is half tau squared g vector, and the resultant is the displacement vector. Again, we have a triangle. We may use SOT, POT, and find angles, side lengths, and in the same way, we won't consider direction properties while handling trigonometric things or anything related to geometry. Side length, we will consider it directly side length with direct magnitude, nothing related to direction or anything. Okay. Now we have a very interesting combination. We'll see it in the next page. Yeah. So we have this equation v equal to u plus g tau. I'll write it once more. U vector plus g vector times tau. Now we will do one thing, we will multiply both sides by tau, see what it does. Sorry, not half, only tau squared with g which scales the g vector part. Okay, so now we have this thing, we can split this g vector tau squared in two equal parts, half g vector tau squared. So we'll write it again. Okay, these two are the same thing. See, now this part is the displacement vector which we saw in blue color. This is the blue thing, S vector. So this is a very interesting property, that final velocity vector scaled by time is equals to, here we'll write the blue thing, displacement vector, sorry, it is not this u vector, we have S vector. Okay, now we'll plot this. How about we should plot this one first, then I'll show how do we come to this thing. Okay, so we'll plot this thing first, this equation, the scaled part, scaled by, the whole triangle is scaled by tau, each side we scale it by tau. So we can directly conclude that the triangle formed by this equation and this equation are similar, and all length we have are scaled by tau. So both the triangles are similar. Okay, so now we'll draw the vector diagram. This is the u vector scaled by tau, like always. Now we'll draw g, not half g tau squared. We'll draw g tau squared, without half. This is the final velocity vector scaled by tau. Okay, now let's see one thing. First, I won't write tau thing, I'll write just the initial, this equation we'll plot first. I'll write only u vector, this as g vector into tau, and the other thing as v vector. Okay, so this is a triangle we have already seen in the previous slide. The moment we scale the whole triangle by tau, the moment we scale the whole triangle by tau, we get a very interesting thing. Now what we get, the median of this side, the median vector of this side will be the displacement vector. Wait, I'll redraw this part so that, because the midpoint is like very okay, no problem, we'll continue with this only. Okay, so the midpoint might be here, kind of. This point might be the midpoint, I guess. It may be wrong, but it's okay for now. For now. So, okay, so the whole g vector scaled by tau squared, is now broken in two parts, two equal parts. So obviously, uh, each one of them will be half gt square. This, okay, I'll show you using the laser. This part is half gt square, half gt square. This part. So now we can. This is also half gt square, and we have seen this thing, v vector scaled by tau is equal to, this thing should be equal to s vector plus half gt square. So the second half g tau square is this part, and the resultant is this one. So the another addend vector should be along this line, which is obviously the displacement vector, as we have shown it here. We'll connect these two, and now we have this vector. Okay, so see, I'll repeat it once. When we were drawing this thing, everything was normal, but the moment we scale it by tau, we get this nice thing, half g tau square, and we use the vector addition property, we get this triangle. Now what's good in this is that we get the combination of both we saw in this page, both the triangles, we get the combination. See, all color vectors we have: red one, the initial velocity vector; the green thing, gravity vector; the blue thing, displacement vector; the, what do we say, this yellow vector also we get, all scaled. Okay, so if these are clear, now we can move to the general projectile. See, we can use these things in normal questions also, which are not of projectile, those which are like 2D motion and all. But for this particular video, I'll be talking only about projectile. In another video, I may discuss about the other ones. We already have lot of questions of the that type in Pathfinder book. Those give lot elegant solution. So now we'll start with time of flight. Okay. So as we know, time of flight is the total time the object spends in the air. That is the time it takes from the point where it is launched to the point where it lands. Total time it spends in the air. So we'll draw the ground using white color. We'll draw the projectile next. It will be like this. We are drawing a bit smaller only because we need to do lot of things here. So we already need lot of space. Okay, so the initial velocity vector must be tangent to the initial point. See, it might be that u vector was this much only. But since we are now interested in the displacement vector also, why? Because, okay, I'll tell you once why we are interested in the displacement vector. See, how do we fix the condition of time of flight? How do we say that the time spent now is equal to time of flight? Why is it not that when the object reaches here, we'll say that the time of flight is complete? We won't say, because the displacement is till here only. The displacement vector is like this much only. Here, when the object is here, we say that the displacement vector is here. When it is here, we say it here, here, or anywhere. So, where will the displacement vector be when the complete flight is complete? So, I mean to say, when the whole flight is complete, it must be like here, horizontal completely. So, we'll draw it in that way only. Okay. So, we'll draw the final displacement vector. It should be like this. Why? Because the displacement, the ball is now, sorry, the anything which we launched is now displaced till here to here, the final displacement. Okay, so the initial velocity vector was like this. Okay, so now we need to see how much should we draw it so that the gravity thing is set aside. We'll erase the extra part once we see it. This is the initial velocity vector scaled by tau. This is I need to draw this perpendicular to the ground. Is this much is sufficient? This is looking like perpendicular. We'll erase the extra part. Okay, so we have the vector diagram using red, green and blue vector. So we remember this was u times tau, u vector times tau, and this was half g tau square, and this was the s vector. Okay, so let me shift it here. Now, as I said, that we have a triangle, and now we can use the normal geometric properties to find various things. Like here, okay, one thing important to mention. See, this was for general time we were considering tau, but now we are talking about a special time, which is the time of flight when the complete flight is complete. So now we'll represent it by, we'll call it tau equal to, sorry, it's not z, it's tau. We'll call it tau equal to t. T is total time of flight. So we'll write it capital T only, not tau. Capital T. Here also capital T square. Capital T square. Yeah. And this angle is 90 degree. Okay, because the anyways the gravity vector will be perpendicular to the ground only. Now the angle of launch was maybe theta, like it's in like it's already mentioned theta. This is the angle which the u times t make with the ground. So for this triangle, let's call it this point as O, this as A, and this as B. So for triangle OAB, sine theta is sine theta is perpendicular by hypotenuse, which is AB by OA. Now we are not using any color code. Why? Because now we won't talk about the vector thing. We'll talk only about the magnitude part. Okay, so we can write it using blue color also. Sine theta is equals to AB. How much is AB? It's half GT square divided by OA thing. OA thing is UT. The T gets cancelled with this one. So we get T as 2U sine theta by G. So this is the thing we get in normal algebraic derivation also, and we get the same thing using geometry also. But you see, this is another way of seeing the same thing. You will develop a new perspective to projectile motion using this geometric method. Okay, so this is the time of flight part. Next, we'll discuss about the range. Okay, so we define range to be the maximum displacement along the line joining the initial and final point. Okay, so we'll draw the ground first using white color. Yeah. Again, we'll draw a small projectile. So again, the initial velocity vector scaled by tau will be no. First, we need to see the range thing. No? So the range will be the line joining the magnitude of line joining the initial and final point, which is horizontal in this case. The next thing is we can like bring the same thing which we were drawing here. We can copy the same thing. The extra part. Okay, so now we have the same triangle. Why do we have the same triangle? We have the same triangle because again we are talking about the end point only, the last point. So we have we have identical vector diagram because it's the same moment we are talking about, the tau equal to t moment. So again in the triangle OAB, we have, using Pythagoras theorem, we have I have left it there. We have OA square is equal to OB square plus AB square. We need OB thing. So OB is root of OA square minus AB square. We write their values. OA is u square t square minus 1 by 4 g square t power 4. And how much is the t? T is equal to 2u sine theta by g. For the maths part, we are not using any color code, okay? We are using any color. OBs are, so it is equal to u square into 4u square sine square theta by g square minus 1 by 4 g square 16 times u power 4 sine power 4 g power 4. What do we get? This gets cancelled, 4, this gets cancelled, it becomes 2. We can with root over it, all of the, we get u square, actually 4u square sine square theta by g square common. We have 1 minus 4, we took out sine square theta root over them. Now this is cos square theta. All of them are squared only, so we can remove the square root and we get 2u sine theta cos theta by g. Sorry, u power 4 it was, no? It was u power 4. It's not u square. U square will be outside the square root. So it's 2. Now we can see 2 sine theta cos theta is sine 2 theta. So we get our famous expression for range using the vector triangle also. Okay, so this is the range formula that we get using the algebra. We get the same thing using the geometry also. Okay, so now we'll see the maximum range analysis. What do I mean by maximum range analysis? Yeah, we have the same thing. We'll use this same triangle only. Okay, one thing we have quite clear here. Okay, I'll take this on another page only. How do we do it? Let me see next. Okay, now observe one thing. We have this triangle u vector tau and v vector tau and this halfway. Can we say, just a second, see the displacement vector, this thing when tau equals to t is r vector only, the range vector I mean to say. Okay, now we'll try to make a parallelogram. How we'll make it? See how we'll make it. We'll again copy the same thing. We'll shift an identical vector to this point. Same thing we'll do here also. We'll select this vector. We'll copy it first. We'll move it here. just want to make a copy. Okay, so now we have another same thing. This thing actually has to be the diagonal part, the S vector. We'll redraw this thing. I think we should redraw it. This is V times tau. Or we'll simply delete this. We'll join the other part, and the intersection part we'll call midpoint. From now onwards we'll call this point as midpoint. This is the half g vector tau squared, and this is half g vector tau squared, and this is the S part. So can we see one thing? Let's call this O. This one as A, B, C, D. So in triangle ADC, can we see that AD vector plus DC vector is AC vector? How much is it now? I should shift it a bit because it's not very clear. Okay, so AD vector is U times tau. DC vector is V times tau. And the AC part is twice of S vector. You see how? Because this much AO is S vector and OC is also S vector. So AC is AO vector plus OC vector. You see how? AO vector plus OC vector is complete AC vector. So AC vector will be 2 times S. So at this point we can say S vector is equals to something into tau by 2, and that something is U vector in red plus V vector in yellow. V vector in yellow is final velocity vector. So we obtain this thing, this particular thing. You can keep in your mind S vector is equal to this thing. Now we'll use it in the other part. We'll import the same diagram here also. Okay, so now we'll move on to the maximum range analysis. As we saw on the content page, the next part is maximum range analysis. We'll use these diagrams for those analysis. Okay, so I'll copy this for the next page. Right here. So what are the equations we know till now? We know S vector is equals to vector plus v vector by 2. Also what we know is v vector minus u vector is g vector times tau. So now we'll replace this tau here. And also, since we are talking about the range, that's the length part, so we don't need the direction property of vector. So we can take mod both sides, okay? So this will be r. And since we are now dealing with normal lengths, we won't use color coding. U vector plus v vector mod by 2. The tau will be replaced by v vector minus u vector by g. Now we'll square both of them. Okay, now we have r square equals to okay. So now we can clearly see, for range to be maximum, this has to be maximum. So for this thing to be maximum, this thing should be 0. U dot v should be 0. What does this mean? This means that the angle between u vector here we have vector only. Since we are not drawing this on the diagram thing, that's why I use the blue color only, but these two are vector right now. I've shown with the white color. Okay, so what we see, the angle between u vector and v vector should be 90 degree for this case, pi by 2. I'll repeat it once more. See, we have s equal to u vector plus v vector times tau by 2. This we already saw how do we get it. And also we have this equation. This is quite old for us now. Now how do we do it? We take mod both sides, so the direction property goes away. Now we have only length thing. Similarly, we get the same thing from here also. We remove the g vector, we get only g because we took the magnitude thing. Here also same thing. So these two are the one. But for expanding, it will be easier to square both sides. That's why I squared them. And see, we clearly get a plus v and a minus v multiplied together, so we get a square minus b square thing. And for this thing to be this part to be maximum, this thing should be minimum. For this thing to be minimum, this thing should be 0. Sorry, yeah, this thing should be minimum, and this thing cannot be negative, so the minimum it can go is 0. So if these two are 0, the angle between them should be pi by 2. Okay, so I'll write this on the next page. Sorry. This was duplicated, I guess. Yeah, so this we have this page, and then we need this here. Okay, after this we'll write this here. for a projectile to have its maximum range, the angle between the initial velocity vector and the final velocity vector should be pi by 2. Okay, so for a projectile to have its maximum range, the angle between the initial and final velocity, velocity vector actually, initial velocity and the final velocity vector should be pi by 2. Also, okay, wait, nothing. We won't mention this. Another important formula for range we'll derive on the next page. We'll again need this figure. Have we missed something? Yeah, we don't have the vector and this here. This should be there. Similarly here also. Okay, now we see this parallelogram. Now we what are we going to do is now we'll first of all write this as range only, because now we are talking about the complete thing. So I'm not changing, but think tau to be t now. Okay, but since that won't occur in the equation, so that this tau will ultimately get cancelled, so we are not worrying much about it. Okay, so what are the two ways in which we can write this area of parallelogram? The first one is dot cross product of adjacent sides. Let us draw the first this. If we take these sides, the area will be this. Just a second. I made an error while drawing the arrow. So this I draw anti-parallel. It should not be anti-parallel. It should be parallel to this. Okay, so we were talking how do we express the area in two ways so that we can equate them and get some relation between two. One thing is half into product of diagonals and the other is the cross product of adjacent sides. We'll write both of them. How? So u vector cross v vector should be equal to half into this diagonal and this diagonal. So this complete green thing is g tau square. Half is half g tau square, half other g tau square. So both of them will combine to give g tau square, and these two will combine to give 2r. And this much is v vector, and we'll take the magnitudes because this side we are expressing in terms of length, so both of them should be length. It can't be that one is vector and the other one is okay. So this was u tau, no? This was u tau. This was v tau. This is b, c, and d. So what do we see? This was not to be written in green. This was to be written in white only. Now what do we see? This tau, tau and tau squared gets cancelled. This 2 and 2 gets cancelled. So we have, what do we have? We have r equals to u vector cross v vector mod of them divided by g, which we can write uv sine phi by g, where the phi angle is the angle between u vector and v vector. So this is also one of the like rare formula we see in our course. Okay. Yeah, and again we can see that this is maximum only when phi sine phi is 1. So that automatically means phi should be 90 degree. Okay. So almost all kind of analysis is done, so we'll move on to the problems. So this is a problem from Pathfinder. We'll see it. We'll give a formal reading to the problem statement. Angle of projection from the maximum horizontal range of a projectile is 45 degree. This is a known fact already. If the point of projection, yeah, this is when the both point we have are on the same level, same horizontal level. That means no vertical difference. If the point of projection and the point of landing are in the same horizontal level, yeah, till here we know already. Determine the angle of projection for maximum horizontal range of a projectile if the point of landing is at a height h above the point of projection, the point of landing is at a depth h below the point of projection. Okay, so we'll start with the first part. The point of landing is at a height h above the point of projection. So we'll draw the ground using white color. Okay, now see, the projectile must be like this. And it should stop here because the point of landing is at a height h above the point of projection. This is the point of projection and this is the height where it should stop, which is at a height h above the ground. Okay, the point of. Now we'll draw the corresponding vector diagram. Okay, we'll shift it a bit. Okay, so the initial velocity should be like this. And the gravity, sorry, this is the initial velocity scaled by tau. Okay, so now we'll draw the gravity vector. This is the gravity vector. This is a complete gravity vector. Sorry, this is the gravity vector squared by tau square, not the half part. Okay, so this is g vector times tau squared, and this part is the final velocity thing. Now the midpoint will be the point of displacement, which should be at a height h from this white line. So this should be around here. which will bisect these two parts in half g tau square. Okay, so now this was the angle of launch, angle of projection. It was theta. And see, we can recall that for maximum range, here we saw in this page, yeah, for maximum range of a projectile, the angle between initial and final velocity vector should be pi by 2. We'll follow the same theory here. So this complete angle, this one, I'll show it. This angle should be 90 degree. So what does this mean? Since this is 90 degree and this is theta, so this must be 90 minus theta, this angle will be 90 minus theta. If this is 90 minus theta and this is also 90 degree, so this one should be theta again. So we'll again draw it theta, and this one is v vector scaled by tau. Now the tan theta part should be for for triangle OAB, I'll write it OAB. For triangle OAB, tan theta should be u by v. Tau gets cancelled, okay? We have a tau also, but it gets cancelled. U by v. Okay, let me show how the projectile exists in this part also. No? It will start from here and it will go like this, and it will end here. And this part is h height. Okay, so this is, I didn't draw it first because I wanted to make this geometry clear first. Okay, this is how the projectile will look. This is u by v. So let's see what's u by v. We can use normal energy conservation of third equation of motion. How do we see it? The work done is minus mgh by gravity. This should be equal to final kinetic energy minus initial kinetic energy. So this should be this should be u square minus 2gh. This should be v. Okay, so the tan theta should be u divided by under root u square minus 2gh. So the theta should be theta must be tan inverse of u by u square minus 2gh. Okay, so the second part we'll see in the next page. Okay, the point where the projectile lands is now h height below the launching level. We'll again draw the ground. Now the red color thing. Again, I'll draw the real projectile after we discuss the geometry, so that things are more clear. This was the initial velocity vector. See, I'm drawing it shorter this time. You'll understand why. This one is the gravity vector. And now this should be the final velocity vector. I'll write this is u scaled by tau. This is g scaled by tau square. And this one is v scaled by tau. Okay, and this should be the final displacement vector, which should be h below the ground. I guess here it should be. See, the last final point of this vector should lie on the midpoint of this thing. Okay. And let's consider the geometry part. This angle is theta. So by similar reasoning, for maximum range this should be 90 degree. This is already 90 degree. So this must be theta also. Now again in triangle OAB I'll show. OAB, in triangle OAB, tan theta should be u tau by v tau. Again tau gets cancelled, u by v, same answer only. So again we'll use energy conservation or work energy theorem, I may say. So work done by gravity right now is mgh equal to half mv square minus half mu square. This one is half, so v will be u square plus 2gh. Okay, now we can write the final answer as theta equals to tan inverse u divided by under root of u square plus 2gh. Okay, now I'll show how the projectile looks. It begins from here and it falls till this point, and this height is h here. This much is h. So this is this is what I want to show. It starts from here and it ends on this, the final displacement vector. Okay, so we'll move on to the next problem. Okay, so the next part is, just a second. Okay, in the book you might see the answer written in bit different way. It may be in the form of sine theta, so you can convert it. If you are given the tan theta, you can find the value of sine theta. Okay, then you will get the answer. Maybe while the authors were solving the book, maybe they have used different method in which we get the answer through sine theta, but in our solution we are getting it through tan theta. So the representation might be different, but the angle should be same. Okay, so the other problem is this one. A student throws large number of small pebbles in all possible directions with equal speeds u out of a window. The pebbles hit the horizontal ground moving at an angle theta or greater with the ground. This is something important. Air resistance is negligible and acceleration due to gravity is g. Deduce suitable expression for the height of the point of projection above the ground. Okay, so see, we are given with something which has only its lower bound theta. The pebbles hit the horizontal ground moving at an angle theta or greater. Okay, so the final velocity vector should make an angle theta or greater with the ground. But now one thing you should see is, we are given the minimum angle theta, so we know the minimum thing, but we don't know about what's maximum, or what we have at some general angle. So we'll try to solve for the part where I have theta only, because or in other words, you may see, like, we want to find the height where where for this case the minimum angle should be theta. For this particular, the pebbles hit the horizontal ground, the angle should be minimum theta. Okay, so what height will give us this result? We need to find it. So I'll show you the case where we have the minimum theta. I'll draw I'll draw the figure first. This is the building we are talking about, H. Now maybe the student throws like here, or maybe here, or like maybe let's keep one horizontal. See, these three we are considering. We'll draw the gravity vector. See the gravity, see, this part should be equal to the gravity vector from red tip to the ground should be equal to the gravity vector below this ground. Okay, so that this one is the displacement vector and this we have as final velocity vector. We'll copy the same. Now we'll draw the corresponding final velocity vector for each one of them. That is along this one. The other one is this one, and the final one is this one. Now you can see, I'll zoom it. See, now you need to see which final velocity vector makes the least angle out of three. You can clearly see this angle theta 1, this angle theta 2, this angle theta 3. So clearly the theta 3 is the smallest. Okay. And theta 3 is corresponding to the is final velocity vector corresponding to the horizontal initial velocity vector. So using this we can conclude that we'll get the angle theta when the initial velocity vector is completely horizontal. Okay, if we take I didn't consider the case where we have this initial velocity vector inclined downwards, but you can do it yourself and you'll observe that still the angle minimum is theta at horizontal initial velocity vector only. Okay, now we'll solve the problem. Okay, let's start. Now I'll draw the situation and we'll draw. Okay, we'll draw the situation later. We have already seen what is the situation. Now we'll draw the velocity vector, the vector diagram. Okay, so this one is the building. Let's consider, we'll draw everything in smaller in size because we have to do a lot of geometry on this figure, so everything should be like compatible with the drawing. The initial velocity should be horizontal. We know why. This one. This is the initial velocity vector. Not initial velocity vector scaled by tau. Maybe sometimes I forget to see, but you guys should observe every time, right? Now the gravity vector is like this. We'll draw this. Okay, let's draw this. We'll take approximation. Okay, approximately these two lengths should be equal. The length till here and now till here, these should be equal. We know why. Now the blue thing should join this to the ground. This is the displacement, and this should join this to the end. Now we want to find this this h height. We'll label everything also. This is half g tau square, half g tau square. Okay, so for triangle, I'll name the triangle first. For triangle A, B and C, let's mark this D, this as O, triangle ABC. Let's okay, so this thing is theta, so this thing should also be theta. So sine theta should be equal to, sorry, tan theta we'll consider it, because AC is V and it's not easy to find V at this point. We can find it, it's not so difficult, because we can directly do u tau square. This AB square plus BC square should be AC square, but that will be more time taking. But we can do that also, okay? That's another method you can try. You can try a lot of things when you are doing it on your own. But right now I should keep it simple. We'll see tan theta. Tan theta is BC by AB here, perpendicular by base. How much is BC? BC is half g tau square plus half g tau square, which is how much? G tau square divided by this u tau. So tau gets cancelled. We get u tan theta by g as our tau. Now we can see, since this is a rectangle because each of them is 90-degree only. So A AOA should be equal to dB. This implies H should be equal to, let's write it with blue color. H should be equal to half G tau square. So how much is this? Oh, you see how in this polygon we can see these are parallel. This is a rectangle only, so in rectangle the opposite sides are equal only. So this is half G u square tan square theta by G square. So G gets cancelled. We get u tan theta square by 2G. This is the height which is required. I'll again explain it. So now this is the height from where if we randomly throw a stone, then the theta is the angle which is minimum that the final velocity vector will make while falling on the ground. Okay, so this is how h and theta are related for this particular problem. Okay, you can replay this part if you don't understand anything, because I think I've explained everything quite clearly. But actually these concepts are a bit tricky, so you need to put some effort on your own also. And if you understand this, it will give you a new perspective towards projectile motion. Okay, so now we'll move to the other problem. So the next problems. Okay, so this question is from Erudov. Last two were from Pathfinder. We still have more problems on projectile motion that you can solve using vector method, but those I leave for you to try, because if you don't try yourself you won't develop the concepts properly. Okay, so let's read the question. Two bodies were thrown simultaneously from the same point, one straight up and the other at an angle of theta, which is particularly given to be 60-degree to the horizontal. The initial velocity of both of each body is equal to v naught, which is 25 meters per second. Neglecting the air drag, find the distance between the bodies at some time t, which is given to be 1.70 seconds later. Okay, so let's understand the situation properly first. This is the ground. One we consider yellow body and another one we'll consider green body. Yellow body was thrown vertically upwards like this, whereas the green body was obliquely thrown. it was thrown like this. So now at every time t, okay, so at every time t, they are at some new position. Like at t1, the position might be this. At t2, it might be this. At t3, it might be this. At t4, it might be this. So lot of points. What the author expects us to find is the distance between them at a given point of time. This thing. Okay. So we'll solve this problem. One thing you must notice is how simple it would be if both of them were traveling on a straight line. It would be a bit simple because we could directly use some triangle geometry and get the answer. Talking about the geometry part only, okay, algebraically it might be something different. Okay, we can find using parametric coordinates. Here the parameter is 0 comma half gt square v naught t plus gt square or minus, but in this part it should be minus only, or anything you can solve it using those things, because the gravity thing is downwards and we are taking the sign scheme to be positive on the upper side, so it should be v naught t minus half gt square only. And here we can take it u cos theta t comma u sin theta t minus half gt square. Okay, but and we can use the distance formula and we can use the distance formula and directly we can get the answer. But since we are talking about the geometry part here, we'll do it in some other way. Now I'll introduce a new concept. Like, concept is not new in a way, but you must have, I don't think a lot of you must have used that concept. Okay, now we'll see this thing in a different way. Now I would like to recall one thing for you. Whenever initial velocity and the initial and acceleration both are parallel or anti-parallel, then the motion is straight line. But when angle between the initial velocity vector and acceleration is not 0 or pi, then it takes some other shape. For example, in this we have a parabola. Okay, for this thing particularly. So we can notice uh, which thing is spoiling our game. Okay, so we can clearly conclude that acceleration is something that's disturbing our shape. So we'll use the concept of falling observer. What do we mean by falling observer? Try to understand this. This is very interesting. We'll imagine that here we have someone, okay, and he's falling down in gravity. No velocity, just no initial velocity, just gravity. At some moment, at some given moment, okay, at t, this person starts to fall at time t only. We don't talk about just before t or just after t. Why? Because it will gain some velocity. We are strictly talking about time t. Okay, so what will this person observe? He'll observe the same distance between them as anyone who stands here. Both the person A and person B, both of them will observe the same thing. Why? Because only perspective can change length. Other than the perspective, nothing can change the length. Okay, because uh, we necessarily don't consider the vector aspect. We just consider the magnitude. Okay, change of frame of reference can alter velocity, acceleration, but it can't alter some length. It can alter some length vector, but it can't alter length particularly, only dimension part. So now this falling observer will notice that this yellow person is moving upwards with only velocity v naught. Why? Because since both are falling, because both are traveling in same acceleration, the acceleration part gets cancelled while relative motion. Okay, so this person will notice that this body was traveling upwards with v naught velocity, no acceleration. Whereas things don't change much for this, but for green part something magical will happen. Now, we may think that the initial velocity was given in this direction. Now we don't have any green g vector. Okay, so the body will continuously travel along this thing only. You understand why? Because the green vector was something which brought the blue vector at some point. Okay, we see if green vector was present, half gt square thing, then the blue vector could join these two ends. Since we have this green thing 0, I'll redraw. Now the green thing has become 0. So the blue vector and the red vector have to be same. Okay, so we got our desired triangle, right? So now I'll clean the page and I'll show how do we solve this. We have a better way to clean the page, but anyways. Okay, I'll draw both of them again. We'll first draw the ground. Yeah. Now the person moving along this thing, and the other guy was moving, making 60 degree of angle. We can't be precise here because it's not showing the angle properly. Yeah, it's stopping after 28.7. Let's imagine this was the 60 degree angle. Let's draw with red only, sorry. We'll draw it using red because the initial velocity vector has to be in the same direction. Okay, so this thing. Now both have same velocity along these lines. Consider this object that this traveled till here. And the red thing was here, the red fellow. Now the distance between them is this. And both of them are traveling, one is traveling with v naught, one is traveling with v naught into t, the other one was traveling with v naught into t only, because both had same velocity, v naught into t. These two are same, and we have an isosceles triangle. So I'll show, if this was 60 degree, this has to be 30 degree. Okay, so the rest, which is 150 degree, should be divided among these two, 75 75. Okay, or we can solve it in general way only. We should not use we can put the values later. Okay, we'll solve using general angles. Let's consider this to be theta only. So this is 90 minus theta, 90 minus theta, and these two are equal. And how much are they? They are 90 plus theta by 2, 90 plus theta by 2. This one also 90 plus theta by 2. Okay, now this is the separation length L. We'll use, okay, I'll mark the triangle ZOAB. We'll use sine rule in this triangle. So using sine rule, what do we get? OA divided by sine 90 plus theta by 2 is equal to AB, which we are required to find, sine 90 minus theta. Okay, OA is V naught T, and sine 90 plus theta by 2 is cos theta by 2, and this is equal to the separation cos theta. So what do we get? We get L as cos theta by cos theta by 2, this multiplied to V naught t. Now we'll put the values. Cos 60 should be half, and cos 30 should be root 3 by 2. V naught 1.7, V naught was 25. We can solve and get the answer. Okay, get the answer. This is the answer in general variables. We can put the values. Okay, so now we'll move to the next problem. I hope you understand this. If you don't, repeat this once, because this is conceptually different thing. Like maybe you haven't seen this before, so it's okay. It's obvious that you won't understand everything at first. You can repeat the part where you felt you didn't understand something. Okay. Okay, I think I made some error. By 2 should be complete on this. Okay, this complete thing should be by 2. And then only we will get theta by 2 will theta, and will cancel with this minus theta, and 90 by 2 and 90 by 2 will be 45, and we'll add to make it 180 degree. Okay, so I'll edit these. The answer was not looking nice, that's why I thought I made some error. V naught t by let's keep it sine theta sine 90 plus theta by 2, and this is L divided by cos theta. Just a second. Sine 90 minus theta will be as good as sine 90 plus theta. So we can write this L divided by 2 sine 90 plus theta by 2 into cos theta by 2, cos theta plus 90 by 2. And this will get cancelled, this with this, and we'll get L as 2 V naught t cos 45 plus theta by 2. We can expand this, okay, using normal trigonometry. Okay, so the next problem, this one is again from Irodov, and again here you must look very carefully to this question, then you will understand the solution. Okay, so two particles move in a uniform gravitational field with an acceleration g. At the initial moment, the particles were located at one point and moved with velocities v1 equals to 3 meters per second and v2 equals to 4 meter per second horizontally in opposite directions. The okay, find the distance between the particles at the time when their velocity vectors become mutually perpendicular. Okay, so now we'll see it. First we'll see what happens in reality before going into the geometrical solution. Okay, so now let's imagine this one, this is somewhere, this is the point where they start to move. This point and this point. Okay, so one moves with 3 meter per second like this. It started like this and now it will move like this somewhere as a parabola, whereas this will have some greater velocity and will move like this. At each point they will have a velocity which we can consider the final velocity. Okay, and the author wants us to know when these two become perpendicular, and at the point where these two become perpendicular, he expects us to find the distance between these two. Okay, you understand how it is happening in real life. Now we'll try to interpret this thing geometrically. Okay, the see specifically for this question, the geometric construct is quite confusing, so you need to listen nicely and try to interpret on your own also once. Also, the geometric calculation might sound new this time. Okay, now I'll start drawing the formal thing. Let's draw a horizontal line once for reference only. Consider this a horizontal thing. Okay, at some point, one starts towards one end. With this velocity. The other one starts with some greater velocity on the other side. Like this. Now we want to draw the gravity from the head side because we want to add like this. But we get two different triangles with one same length side. So intelligent thing should be that we should join these from tail to tail. We should join these to head, and then we can draw one single green vector, and we'll have our work done. So we'll do the same thing. Now we'll draw the velocities head to head like this. Okay, just a second. One we'll draw like this, the other one we'll draw like this, slightly larger. Now we'll add one common gravity vector. We'll remove this, we don't need it now. Okay, so this one was V1. Tau also. Because since we are talking about the scaled velocity, we want it to be since we are talking about the final velocity vector, that's why we are scaling to obtain something like final velocity vector. Okay, else we'll get the displacement thing. We need to get both of them, that's why. And this thing should be v2 vector with tau scaled by tau. I think we should make this line a bit shorter so that we'd obtain 90-degree. Okay, a bit longer. Okay, first we should draw and then we should see. So our final velocity should look like this. One should be like this and the other one should be perpendicular, just like this. These two should be perpendicular. And the displacement vector is somewhere. Now the displacement vector is quite confusing in this problem because here it should be on the midpoint and again here it should be on the midpoint, but the distance is not zero between them. Why? Because they are traveling on two different sides, but for our simplification we are drawing it on the same. But we should keep in our mind that r1 wait just a second. r1 vector minus r2 vector mod is our answer. We should keep in our mind. This one is r vector, r1 vector, and this one is r2 vector. Okay, so now let's see v1. Now for this triangle, I'll mention o, a, b, c and d. For triangle ocd, wait, we'll consider the complete triangle obc. For triangle obc, v1 vector tau minus, because now the vector is in different direction, v2 vector tau plus r2 vector should be equal to r1 vector. Now take r2 to this side. We'll get r1 vector minus r2 vector mod as v1 vector minus v2 vector. Okay, now we should find tau. How we will find it? So I'll tell you a geometry thing. It's whenever we have a right angle triangle, consider this to be right angle, and we drop a perpendicular on its hypotenuse like this. Always remember, the product of this length and this length is equal to this length squared. I'll write it again. O A B C. We have OA into OC equal to OB square. How you can prove it? Wait a second, I'll prove it here only. Consider this as theta. This will be 90 minus theta. So this will be again theta. So this one will be 90 minus theta. Now you see, you can clearly see these two triangles are similar. Why? Because both have three same angles. So OB divided by OA, OB divided by OA is equal to OC divided by OB. First, what we notice, triangle OBA is similar to triangle OBA is similar to OCB. OBA is similar to OCB. Okay, so we have this thing. What we can say now, OB square is equal, when we cross multiply, we say OA into OC. I'm not sure, but I guess these are named after Euler only. Euler's identity, maybe. We have a lot of things in maths named after Euler, so I'm not sure, but I guess this thing is known as Euler's identity only. But we just need to apply this. We don't worry much about the name. Okay, just a second. I think I should leave this like this only. You can see it. Yeah, so if we apply the same thing, we have actually the same thing, just flipped downwards. See again, OAB is a right angle and we have these two angles 90 degree only. So we can say what? We say AD square should be equal to OD, sorry, OD, OD into BD, and OA is, sorry, AD is GT square, G tau square squared equal to V1 tau V2 tau. So G square tau power 4 equals to V1 V2 tau square. What we get? We get tau equal to V1 V2 root divided by G. Okay, so now we have this. We have got this tau, and the vector difference between V1 V2 is how much? See, now we are close to the final answer. Now we are trying to interpret this mod of V1 minus V2. Try to think. Okay, I should copy this down. I could not copy the arrow thing. I'll make it again. Now we should copy this thing. Now we have said that we want a difference, so we need to draw the uh, minus v2 vector. I'll again copy this. So now if we replace the arrow, sorry, if we move this arrow from this end to this end, we get minus v2 vector. So the addition of these magnitude will give us v1 minus v2 mod with tau. So what's the final thing? The r1 vector minus r2 vector, which was said to be v1 minus v2 into tau, but what we have right now, v1 minus v2 vector is actually equal to v1 plus v2 in magnitude. The magnitude of this is equal to this. So what we have finally, distance between two of them when the final velocities, not final, we are considering to be the final because that's the end moment of our analysis, between them when the velocities are perpendicular is v1 plus v2 into tau, which was, we use the perpendicularity of the velocities for finding the tau value. This is the time when the both velocities will be perpendicular to each other. Okay, so this was the derivation for that thing. Okay, there are more two such relations which I leave upon you to find. So this is the last question. This is from SBT, I guess. This question is also easy and it's not much related to this thing. Oh yes, we can relate it with one of our theory which we have covered in our class. That will help you revise it. Three stones are projected simultaneously with same speed u from the top of a tower. Stone 1 is projected horizontally and stone 2 are projected making an angle theta with horizontal as shown in figure. Before stone 3 hits the ground, the distance between 1 and 2 was found to increase at a constant rate u. The distance between 1 and 2 was found at a constant rate, increase at constant rate u. Okay, obviously they are giving us the relative velocity indirectly. So we need to find theta. Okay. And they are also thrown with speed u only. Okay, so this is now very easy. First one was moving like this. One was moving like this. Both with same speed. And one was moving like this. This was 2, this was 1, this was 3. Each of them being u not u sorry not u not u and u. The distance between 1 and 2 was found to increase at a constant rate 1 u. So the distance between these two are increasing at constant rate u. So this, if we complete this triangle, this is also u only. What we get? So we get an equilateral triangle. So 100% this theta should be equal to 60 degree only. Okay. Now we are required to find the rate at which the distance between 2 and 3 increases. This is u, and this is also u. This must be u only. This is u. Okay, now let's find this yellow thing because this is our answer in this vector triangle. How we'll do it? See, this is a parallelogram. Leave parallelogram. We'll use simple trigonometry. We have this thing perpendicular, this thing perpendicular. This is u and this is 60 degree. So this must be u sine. We yeah. Is there anything more elegant we can do right now? Okay, we can use one fact that this should be root 3. Okay, this is a direct result we already know, or you may find it using trigonometry also. I'll show how. This is O A B C D. For triangle AOD, sine theta is equals to OD by AD, and OD is what we need to find, and AD sine theta sine 60 is our OD. So OD is u root 3 by 2. Same thing we get in this thing also. So OD and OB are equal. So BD was our answer, which was u root 3. So for this we have the answer as 60 degree. For this we have u root 3. Okay, so this was the last question for today. I hope you understand the concept. See, somewhere this is just a method. Somewhere it will give more elegant solution, whereas somewhere this may become lengthier. See, for questions like this, uh, see, in most of the case we have seen it has made easier only. Like this question, I think the vector method makes it lot easier. Okay, see, in each part of them you can use geometry everywhere. This is, see, the concepts which I taught in this class are true, but it's not useful everywhere. You need to pick questions where you can use these concepts and get answers very quickly. For example, in this question we had to draw the diagram and we could clearly see that the angle was 60 degree. Okay, so this was the beauty of this method which we see in this question. This is not related to, this is related to projectile, but somewhere we can use it somewhere or the other. See, if you are confused with the gravity part, again you can use the falling observer method. You can imagine someone is falling here, or it's not required also, it's not required. Okay, so I'll be uploading more videos on this channel. You can subscribe so that you know when I post some video. Okay, so thank you. I'll meet you in the next video. Bye.